We can see moving objects like the vehicles in the street, leaves in the tree, water in the river, and ball rolling in the floor. People go shopping, dogs are running, and birds are flying. They all obviously tell us they are moving. But in science, describing motion requires careful use of these definitions. When can we say that an object is in motion? How do we describe the motion of an object? To answer these questions, let us describe the motion of an object in terms of distance or displacement, speed or velocity, and acceleration. Before you will be able to describe motion of an object, you must first be able to tell exactly where it is positioned. Describing exact position entails two ideas. First, describing how far the object is from the point of reference. And second, describing its direction relative to that point of reference. A point of reference, also known as frame of reference, is important in determining motion. To say that something is moving, we need to have something stationary to compare it to. For instance, when you look at the window of your vehicle, you can say that you are moving as you pass along the trees, buildings, people, or any object outside the window. They serve as your points of reference. Consider this diagram. The positions of the objects are described in the diagram by their coordinates along the number line. Analyze and answer the following questions based on the diagram. 1. What is the position of the dog? 2. What is the position of the tree? Number 3. What is the position of the dog with respect to the house? And number 4. What is the position of the tree with respect to the dog? How is that so? Applying what you have learned in Mathematics 7 about the positive x and negative x coordinates, you need to add numbers with the same sign and subtract those of different signs, taking the sign of the larger number. In science, motion is defined as the change in the position for a particular time interval. You can start describing motion with the question, how far did the object travel? There are two ways to answer this question. First is by getting the total length of the path traveled by someone or any object. I want you to meet our lab partner today, mBot, which will help us describe motion. If mBot traveled from rest to 2 meters to the east, then traveled 1 meter south, then another 2 meters to the west, what is its total distance traveled? That's right, it traveled a total of 5 meters. The other way is by measuring the distance between the initial position and final position of the object. How far is mBot from the initial to its final position? Great! mBot is just 1 meter to the south. In physics, the first measurement, 5 meters, is the distance, which gives us the total length traveled, while the other one, 1 meter to the south, is the displacement, which is the shortest distance between the object's two positions, like the distance between its point of origin and its point of destination, no matter what path it took to get to that destination. Notice that in the first answer, we only use the magnitude 5 with its unit, meter. This is an example of a scalar quantity, which is defined as the physical quantity that has only magnitude, On the other hand, the second answer, 1 meter to the south, is an example of vector quantity, which is the physical quantity that has both magnitude as well as direction. When a graph is plotted in terms of the distance traveled by the object and the time it took over such distance, the graph can be called distance-time graph. If the graph is plotted in terms of displacement and time, it is called displacement-time graph. Look at this example. Analyze the graph and answer the following questions. First, what is the displacement of the object after 2 seconds? 2. What is the total distance traveled after 6 seconds? 3. What is the displacement after 6 seconds? 4. How will you describe the motion of the object? First, between 0 seconds and 2 seconds. Second, between 2 seconds and 4 seconds. And third, between 4 seconds and 6 seconds. The previous problem is connected to the question, how fast did the object move? This information can be provided by the object's speed or velocity. Are you familiar with these traffic signs? These signs tell us the maximum or minimum speed limits allowed by law for road vehicles. In general, the minimum speed limit in the Philippines is 60 kilometers per hour, and the maximum speed limit is 100 kilometers per hour. What are the units used in the examples of speed limits? What quantities do these units represent that are related to speed? The questions asked previously has something to do with speed. It is a scalar quantity which is defined as the distance traveled divided by the unit of time. Its equation goes like this. The units of speed can be miles per hour, kilometers per hour, or meters per second. In describing the motion of an object, we do not just describe how fast the object moves. We also consider the direction to where it is going. Speed with direction is referred to as velocity. It is a vector quantity which is defined as the change of its displacement with respect to a frame of reference per unit of time. Its equation goes like this. The units of velocity like speed can be miles per hour, kilometers per hour, or meters per second, except it has direction. This sample weather bulletin shows the importance of knowing not just the speed of the storm, but also its direction. Study this weather bulletin and answer the following questions. Number 1. Which is the maximum wind speed for the circular motion of the typhoon winds? 2. Which is the speed for the motion of the storm along the path? Number 3. How important are speed and direction in determining the weather forecast for the next hours? Objects do not always move at constant velocity. Observe the motion of Miss Leia. Write it in your observation notes. That's right! Miss Leia started from rest, then moves fast, afterwards moves slowly, then takes a rest. This is referred to as the change of velocity per unit of time called acceleration. Its equation goes like this. The unit of acceleration can be derived by dividing the meter per second by the second, giving the unit meter per second squared. An object with an increasing velocity and is changing its direction is accelerating, while an object with decreasing velocity is decelerating. Now, let us apply what you have learned in this lesson. We're learning task 1 entitled My Home to School Roadmap. Read carefully and follow these procedures. We're learning task 2 entitled Fun Walk. Read carefully and follow these procedures. Rearrange the jumbled letters and match them with their corresponding definitions. Write a 2 to 5 sentence reflection at the end of the lesson. Please do not forget to subscribe to our YouTube channel, Math Cycle, like the videos, and hit the bell button for updates. I hope you learned today's lesson. On the next episode, we will be creating and interpreting visual representation of the motion of objects using flip charts and/or motion graphs. This is Sir Michael Leonard, your science teacher. See you all next time.